I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hello and welcome to the Materialism Podcast, an exploration of the past, present, and future of material science and engineering. My name is Taylor Sparks. I'm a professor of material science and engineering at the University of Utah, and I'm joined by both Jared and Andrew. Guys, how are you doing?
Good. Yeah. I've been away for the entire summer out east, and I finally have returned to the west, and it feels good. You know, the humidity was actually kind of nice in the early summer, and then once we got peak, it became pretty intolerable. And plus, it's hard being away from what you're familiar with. I was basically just on a mattress on a floor in an empty room, the ideal male living space as it's referred, and I got a bit sick of that. I wanted my old room back.
I spent 3 summers in grad school in China where it was a very similar situation. It's really fun for a while, but you always want to come back home, I think. And Jared, how are you doing, man?
Speaking of grad school, I'm starting grad school.
In aerospace, right?
Yes, I'm starting my master's in aerospace engineering at the University of Illinois.
So if you think that we should do an aerospace materials episode, why don't you shoot us an email? Say, hey, Jared.
Oh,
turn that into an episode, my
man. Give
man.
some time to work up to it, but yeah, definitely. Before we get started, we want to give a big shout out to this episode's sponsor, American Elements. Now invent.
Well, today, guys, I'm psyched that we're all 3 together because we have a cool episode. I'm guessing that everyone out there has by this point seen Oppenheimer. Everyone but Andrew. He's not doing it. But for those of you that did see Oppenheimer, first off, it's a great film. But yes, you might remember when he's at Los Alamos, right? Oppenheimer's doing Oppenheimer things. And he's like, we have to get some stuff done while we're waiting for the materials to make the bomb. And if you remember the movie, they have the giant glass jars and they're putting marbles in it. Mm-hmm. And that represents, their progress towards the amount needed to build these bombs. So there is a plutonium jar and there's a uranium jar, right? And if you're like me, I watched that movie and sort of just assumed like, oh, well, the Met Lab in Chicago, the metallurgical laboratory is famous with, right, the Chicago pile, Enrico Fermi. Well,
it's worth noting that that's the enriched stuff that they're talking about there because they actually mention in the movie coming from Oak Ridge.
So, but regardless, I thought that this came from Oak Ridge or University of Chicago. It turns out that that's not the case. And we're excited to tell you about somebody who didn't show up in the movie. He didn't show up in the book, American Prometheus, which I read, but was really absolutely critical, not just instrumental, but like he was critical in turning out pure uranium, which we needed for all of that. And it's a guy named Harley Wilhelm in the most unlikely of places, actually at the University of Iowa, what is now Ames National Lab, right? Mm-hmm. It's actually one of our national laboratories. It's a great place where they still emphasize growth and synthesis and fabricating things. But back then it was just a college. It was a land-grant university in kind of the middle of nowhere. But because it was sort of nearby to Chicago, which was the home of the metallurgical lab, they knew that they needed to be making this alloy, but they actually didn't have the furnace. I think this is fascinating. Arthur Compton, Nobel Prize winner, right? Enrico Fermi, all these people, but they don't have a furnace necessary for the metal smelting to actually start melting these alloys. And so they order one, obviously, but it's not going to be there for months. So instead they start looking around. They say, who's nearby that has one of these?
Well, then there's a bit of intro to that, actually. And I think it's a really fun story, is the guy who was actually at the time running the Ames School for the Physical Sciences, I think is what they called it, which only had 2 people.
Yeah, it was a chemistry department, but this was like the sub area of physical chemistry.
Yeah, physical chemistry is what it was a guy named Frank Spedding. And there's a really interesting backstory where Frank Spedding is giving a speech in 1933 at the Chicago World's Fair, and I believe he's accepting some award for his work in rare earth metal or some sort of rare earth element work. So once his speech is over, a guy named McCoy walks up to him and says, loudly, how would you like to have a pound of europium and 2 to 3 pounds of samarium?
So hold on a minute, because just to put this in context, back then, there was no American Elements, hello, our sponsor, right? That could easily turn out, high purity, quality grade stuff in sort of the amounts that you need. This was sort of an unthinkable amount to get access to something like that, especially for somebody like Spedding, who did research in rare earth metals, right?
Yes.
Who did spectroscopy, and like getting that was a big deal. Because, again, they didn't have people like American Elements back then.
Yeah, and he even says at the time he just thought the guy was crazy, and he didn't know who he was. He just knew his name. So he gets back to his laboratory at the University of California, Berkeley, and that's when he learns that this guy is the vice president of the Lindsay Light and Chemical Company. And I guess when they're doing some separation processes for something that they need, they kept getting trace amounts of these elements, and they had no use for it. And McCoy, someone who's interested in the sciences, offered it to someone he thought would actually have use for it. And so they formed this bond, and he gets his 4 pounds of rare earth metals.
And that connection is why they thought of reaching out to Frank Spedding then when they needed somebody to actually start making uranium then.
What happens is Arthur Compton reaches out to McCoy because McCoy was someone he used to work with at the University of Chicago.
Gotcha.
And he says, come work for me. And McCoy goes, no, I'm okay. But I know a guy who's really good with rare earth metals. This is his name. And so they reach out to Spedding. Spedding comes down. And when they're having this conversation saying, oh, we don't have a furnace, Spedding goes, oh,
I've got one.
I've got one.
And I think
I've got a whole team of people who can work on it. Now, he shouldn't have promised the team. There was one other professor, and I guess they say later that he had no power to actually devote school resources to
absolutely.
the government.
They ended up having to go back to the university president, right, who was only relatively new to the job. He's been there for 5 years or something. And they basically say hey, the federal government, and we can't give all the details on exactly what this is, but has this massive project if you'll let us get release. But they ended up getting release time from teaching in the middle of the semester. Remember, these are the only 2 physical chemists at the school. So they just cancel the classes, I guess. I guess it's wartime, right? But they cancel, and these 2 are given the freedom to begin this top secret project. They hired their PhD students as the workers on this project. It's interesting. There's a part we're referring to this book called Wilhelm's Way, written by the granddaughter of this Harley Wilhelm and everything that we talk about today. But it has some really fascinating anecdotes. For example, at one point, it says that they went to the library and they found that all the chemistry and physics books were gone because they were afraid that they were going to fall into the hands of Germans. Now, I don't know if the Germans, who were quite technologically advanced, really need to go to Iowa State University and grab their books. But still, that shows the level of seriousness that they were taking this threat. You got to put yourself we have this hindsight now where we're so far removed from it. I don't think we grasp how scary this was. Everyone knew that it was possible. And so there was this race was on to make this bomb first. And nobody wanted to tip their hand on how much is, happening, how far along are they, who's working on it and where, for fear of sabotage and spying.
Not to go back to Oppenheimer, but that scene where they first find out about the sustained reaction.
Right?
And
they immediately realize, oh my gosh, that's a bomb.
Yeah.
So I think this is fascinating because here you have this middle of nowhere university with 2 faculty and a furnace. is essentially what this was. And they are now going to be competing with the best of American universities. Princeton was trying to do this. Columbia was trying to do this. Major corporations like Westinghouse were trying to do this. University of Chicago, right? And yet we're going to see that over the course of the next couple of years, Wilhelm and contributions from Spedding and others led to the actual discovery of how you're going to make pure uranium in ingot form, which is what you need if you're going to actually make nuclear power and weapons.
And I think maybe the contributions, this is an interesting time to talk about something that really stands out in this book and in the story is throughout this book, throughout explaining this episode, we're going to talk a lot about everything that Wilhelm did. But if you look up what happened, you will see that Spedding is equally credited in this. And so the book, is written by his granddaughter, as we said, and the book does go a little bit out of its way to tell you Spedding wasn't there for this, or Spedding was actually...
Sometimes in his own words, right?
Yes.
Spedding, in his own words, said that he went to Chicago to be the liaison with the Met Lab, and he left Wilhelm behind at Ames, and even said that he stayed back as the quote-unquote CEO. And it's pretty clear that he did do the day-to-day, and so it becomes a little bit tricky to divide out credit on who did what. And I'm kind of less interested in that. To me, they both were pretty instrumental.
Yeah.
Maybe Wilhelm had a more important role to play. But it's still a cool story because neither of them show up in the history books, at least in the common knowledge of what happened.
Yeah, and I think it just plays into the interesting conversation of credit, and who gets it and stuff. But I think it doesn't matter because both were so instrumental, because without Spedding, Wilhelm would have never gotten the chance, and without Wilhelm, Spedding may not have gone anywhere.
100%. So let's now we've got that sort of backdrop set. Let's talk about how uranium was actually being fabricated. Back then, when they wanted to make pure uranium, this was not a trivial process. Like I said, some of the brightest minds have been out there, and there was a couple of approaches that seemed to work, but they couldn't make ingots. They could only make powder. For example, they could start with uranium oxide, right, the common mineral for uranium as a precursor, and they could react it with calcium hydride, and then you'd end up with a calcium hydroxide, right? Slack lime, I think they call that, or slaked lime. And you'd get uranium powder, but now because it's in powder form, it is highly pyrophoric. It is going to react with oxygen violently. It is flammable. In fact, there's stories about when they were shipping it to Columbia that the entire transit went up in flames. So not a great option. And then we've got Westinghouse. They had a process for making it. They started with uranium fluoride in molten calcium chloride. That does not sound like a nice mixture. And they would catalyze it with sunlight, but this was crazy slow. It said in the winter, for example, it would take days for a few rice-sized pieces of uranium metal. So tricky to sort of scale that.
Yeah, the story was kind of interesting. They would basically just put these in massive vats on their roof.
Yeah,
and just allow
the
sunlight to work on it or catalyze the reaction. I kind of wonder why they didn't use some sort of artificial light.
Yeah, so this is actually really funny. Andrew and I, we were kind of, spitballing before the episode, and we arrived at this really weird conclusion, which is the Westinghouse electric plant that this took place at was a lamp factory. And what lamp had they invented just a few years prior? The first ever UVC lamp. So they had an ultraviolet lamp, but yet they still used the sun.
Makes you wonder why, right? If it was too expensive, they couldn't scale it. This was early days of UV light, I suppose.
Mm-hmm. Also, I don't know, because it's only the C wavelength. I don't know if maybe you need the full wavelength of ultraviolet for it to work. Or
don't know.
But even though it was so inefficient, they marched.
Yes.
They made quite a lot of uranium with this process.
So Compton, this Nobel Prize winner that was at the Met Lab, he gave them a contract willing to pay $1,000. Remember, that's $1941 too. $1,000 per pound of uranium, which just for the Chicago Pile experiment, that would have cost in today's money $175 million to perform that single experiment, because they had no other alternative, because Wilhelm hadn't figured out the way that he eventually figured out to make the stuff in bulk far, far cheaper. So there's some other problems with powder. The biggest one is that it oxidizes, right? And you go from pure metal to right back to the uranium oxide that you started with when it undergoes this reaction in air. So then you either have to seal it, which is still tricky because when you open it, it's more likely to catch fire. Trying to prevent air access is any of our listeners, hopefully, I'm guessing some of them have done this, they know how hard that is to do airless transfer, for example, of components.
There was actually a really funny story where they, I think it was maybe during one of the shipments, it actually arrived perfectly safe, and they had these cans, and they opened the first few, no issues, and then I guess in the coming weeks when they would open them, they would just light on fire.
Yeah, so it was really a non-starter. They knew that they had to get to a bulk, and actually Wilhelm pointed this out. When they did grow something a little bit bigger than a powder, and they looked under a microscope, that's when he realized, this looks more like an aluminum or like oxide, where it forms a semi-passivating layer. Now, it will continue to oxidize all the way through, but slowly. So it's not as good as aluminum. It's not as bad as rust. It's something that you could potentially imagine a scenario where you clad it with something. So they tried starting to clad it with all sorts of things. They tried lead. Lead didn't wet, and when they roughed the surface and it did stick, then it reacted, which wasn't good. So then they were trying aluminum. And it was along this line, I think, that they realized, if you're adding these other agents, right, you could imagine that the other agent, maybe it's a reducing agent, actually, and you could just clad the oxide and have it reduce it to form the uranium metal all in one step to form now a bulk component.
Yeah, uranium's tricky. With that electron configuration, it'll react with almost everything.
And what I found, I loved reading this book. First off, it's way more scientific and chemistry heavy than I expected. It's actually really good treatment. And I love seeing how they dealt with these problems, because nowadays, in hindsight, we have the solutions, but they didn't have them. So it's fun seeing how they approach the problems. And at one point, it even talks about him reading this book by Pilling and Bedworth. And anybody who's taken my Intro to Material Science course, right, knows Pilling-Bedworth ratio is the tool that we use to dictate whether something will oxidize, right, if it's a passivating layer or a non-passivating layer. Here he's using that exact same resource that our students today would use, which I just think is so cool. So they had some ideas about how to clad this, but they also needed a way to actually cast it. And if anybody here has cast anything, now you've got this highly molten metal oxide. What if that sticks to the crucible? Or what if that sticks to the cast form? So they ended up trying a bunch of things and finally settled on, if you take uranium oxide and you melt it, and then you pour it into graphite, this actually works okay, especially if you do it under vacuum. But there were still lots of instances of it sticking to it. And they actually had to take the molten stuff and pour it through a carbon grill to actually cast this metal. So in other words, they are melting uranium oxide, not uranium metal at this point. It's uranium oxide. And they're pouring that from a carbon graphite crucible through a graphite grill to make sure no impurities are there into another one. And in this process, occasionally, they would end up with broken crucibles or crucibles with uranium stuck to them. And so they would basically throw them out the back of the building. But remember, this is happening at a podunk university in the middle of nowhere. And you get enough of these piling up, and sooner or later, people are going to start to wonder, what's going on at Ames? Is this actually education, or is something else going on? So they started taking secrecy pretty seriously. Remember, this is happening in like a little makeshift building. This is not like the National Lab of today. This was basically a shed that they were working out of.
Uranium oxide's non-trivial to melt too. Its melting point's about 2,800 degrees Celsius.
Yeah, no joke. No joke.
Yeah.
In any case, so at the time when they started working on this is now once they realized that they're going to be doing something that's in service of national defense, students that were working there were not eligible for the draft.
Mm-hmm.
And so they had this awkward bit where they couldn't tell people what they were working on because they didn't want spies to come and watch what they're doing. So they had to pretend that they weren't doing anything national security related. And yet the students working there were not eligible for the draft. And so they were looking like draft dodgers, right?
Yeah.
And he had to tell them like, hey, if you guys spill the beans, you will be in the war. You're going to be sent to the German front lines, right?
Yeah. There's another really funny story about security where his kids, this is before it got really intense, his kids were allowed in the lab, and I guess, I think it was his daughter was playing with the safe that they had where they kept their classified journals, and she proceeded to guess the combination and open it, and she got in big trouble for it. Now, I think she'd said...
It might have been Max. It might have been the son Max.
Okay.
Well, they shouldn't have made their password 1, 2, 3, 4.
Well, so the thing was, obviously I can't remember which kid it was, but the kid had said, that was just my gym locker combination.
Too cool.
Oh, that's funny.
Yeah. But that I guess that led, I think it was, he said something like, if my kids can do it, a spy could do it. And so they started building secrecy walls and getting really
well, and he started taking like secrecy very seriously. In fact, he was known to sort of talk in his sleep. Mm-hmm. During the duration of the war, he did not sleep with his wife, right? He actually slept in a separate room just because he knew how devastating it would be if word got out of what they were doing there. So he took it very seriously. In fact, he got a little paranoid. It sounds like he was worried about people in bushes and people overhearing and
yeah, a German family moved in across the street, and I guess from then on, he'd always noticed that the oldest sibling of that family was watching him through the windows whenever he'd come and go, and so he was worried that it was a German spy watching him.
Right. And there were some other interesting things going on. For example, they already knew that boron, so Enrico Fermi has this crazy idea like, okay, what if the pile goes out of control and it's too much power and we need to like turn it off? At one point, he actually suggested putting like TNT in the middle of it and we could just like blow the pile up. Maybe not a great idea, but some cooler minds prevailed and they realized that boron, right? Boron, as we have talked, if you've listened to our episode on nuclear fuel, for example, we talked about boron. It is something that can absorb those neutrons and stop the chain reaction. Okay, but if you're trying to make pure uranium, boron is like the worst possible thing to happen because they're trying to purify it so that reaction happens in the first place. And it turns out back then in the early 40s, boron was kind of all over the place. They would use it in detergent, so like laundry, borax, right? And so they actually had to have a separate laundromat inside their facility. People would come to work, change their clothes, wear their clothes that they're going to be working with uranium with. This was not washed with borax, and they would have to shower before leaving, leave their clothes there, put their other clothes back on. Remember, trying to keep all this secret as possible. Pretty wild.
I think some of it was also, he had said that he didn't want to ask them to change their home lives or something like that.
Yeah.
So he just figured have it all done there rather than make noticeable changes at home.
So in any case, we get to the point where they now have a way to cast it. So now they have ingots of uranium oxide. How are you going to convert that to what you need? So here's where the story gets pretty interesting. It starts talking about thermite examples. Andrew, describe thermite reactions in general that people might be familiar with.
Yeah, there's quite a few. I mean, the most common one, if you just Google it online, you have an iron oxide mixed with aluminum. So
aluminum metal. Aluminum metal.
Aluminum is going to want to grab that oxygen very readily. It's a highly exothermic reaction, so it generates a lot of heat.
Leaving behind the iron metal.
Yeah.
So he had the exact same idea. He's like, well, let's do that with uranium oxide. Let's grab something that is going to be the reducing agent. leaving behind pure uranium metal. And they tried it with aluminum, but it left like these globules of aluminum metal. It didn't react properly. They tried it with magnesium, and it was crazy explosive. Actually led to an explosion, right? And then they find this 1926 paper in the journal Industrial and Engineering Chemistry from these professors in New Hampshire, I think it was, where they did this. They started with uranium chloride, and they added calcium. The calcium pulls off the chloride, leaving behind uranium metal and calcium chloride. And this will actually produce pure uranium. The problem is that the calcium chloride byproduct is hygroscopic. It's going to pull in moisture. That moisture is going to react to the uranium, so it's not ideal. But this was an inspiration point for Wilhelm. He's like, okay, what if instead of that exact scenario, what if you do fluorides instead of chlorides? So uranium fluoride plus calcium. When the reaction takes place, you're left with calcium fluoride. And these are non-volatile, non-hygroscopic. And so they load it up. They've got this pipe bomb, basically. It's 12 inches long, 4-inch diameter. So picture like sort of like a football-sized thing. They put the stuff inside of it. They lined it with calcium oxide lime so it wouldn't react to the pressure vessel. They used a spark plug as the ignition source. They didn't know how big the explosion would be. Like technically thermite reactions, if you've ever seen like tannerite blow off, like these can be big explosions. So they've got it out in the field away from their building. They're hiding behind the corner of it. And they see the reaction. They start monitoring the temperature. It starts vibrating. It's bouncing around. They see the temperature spike. They know a thermite reaction is happening. And then they have to wait hours. Can you imagine like the apprehension, the excitement for it to cool down? Because they know it'll oxidize if you open up when it's hot. But once it's cool, they open it up and there it is, the world's first little ingot of pure uranium. Never been made before.
And if you want a little bit of irony, thermite and thermite-based purification was actually patented by a German in 1895.
Oh, how about that?
Named Hans Goldschmidt.
Come back to get him.
Yep.
You know, what's kind of interesting is I was doing a bit of reading on what was going on in Germany. And if you're interested, if you've got, it's Friday, you're bored tonight, you're not doing anything, you can go home and you can read about the Alsace mission, which was the USA and the Allies' mission to basically try to seize German uranium production and figure out what they were working on. And it turns out that they actually didn't put that much money into this. And
so we were sort of afraid of nothing, really. They weren't that likely to create the bomb, though, you're saying?
In the course of the mission, they ended up seizing all of Germany's uranium stockpiles, and then they went and actually found where Heisenberg and various other people were working on this, and it turns out they hadn't made all that much progress. And afterwards, some of the members of this Alsace mission were commenting that the U.S. probably spent more money on this mission than Germany put into the entire project.
On the recovery mission, let alone our Manhattan Project.
Mm-hmm.
That's wild. In any case, coming back to here, that was the big discovery, right? Now, after that comes the engineering, right? There's the science and there's the engineering. The engineering was like, okay, so you made uranium, but your yield was 7.5%. That's not a very good yield. So they had to figure out how to get rid of the calcium. Okay, so you can wash it in acetic acid. That will leach out the calcium. And then they had to figure out how to get the correct ratio of stoichiometry so that you don't have byproducts. Okay. And then you have to figure out vacuum sealing. And really, that's not practical for scaling. It'd be much better to do this in air. So they had to figure out how to do that. And they work on this, and eventually they're able to cast now a big ingot. It weighs 11 pounds. They think it's pure uranium. It's 2 inches in diameter and about 6 inches long. And it finishes, and they're so excited to take this to Chicago because remember, the pressure's on. Like, if you've seen Oppenheimer, you know like they were against the clock in a major way. So every minute counted. They finish this thing. It's still hot, and they're cooling it down with turpentine. And then they run and they board the train. He puts it in just like wrapped in a cloth inside of his briefcase. And he's so worried on the sleeper train to Chicago that he actually sleeps with it in bed with him, which is kind of awesome to think about. They get to Chicago, and Arthur Compton says, like, he's obviously thrilled, but he's skeptical. He's like, okay, if that's a big old ingot like that, he says, quote, I'll wager there is a big shrinkage cavity inside. Now, why would there be? As you guys know, most materials, when you heat them up, there's thermal expansion. So if you cast this thing into a cavity and then you allow it to shrink upon cooling, it's either going to pull away from the walls, or if the bonding is stronger between that interface, it'll actually pull away from itself in the middle and leave a cavity. Cleverly, Wilhelm had come up with a really clever approach to this. He actually had a casting mold that had a hemispherical dome on the top, and when he cast it, he heated the casting base less than the part above. The hemispherical part above was heated higher, so it was molten, and the bottom was allowed to solidify. So as it was solidifying and creating a cavity, more liquid uranium was pouring into it. Super clever. Like, this is engineering stuff, but it's super clever to make sure that you avoid the cavity inside. One thing I think is awesome about this is, okay, so the guy's skeptical, but he wants proof. So he wants him to cut it open and see if there's no cavity inside. Well, remember, when they left the lab, it was like hot out of the die, and they had poured turpentine on it to sort of cool it down. And now you're going to put it, I don't know why they use turpentine, but anyways.
I was wondering that too.
In any case, now that you're cutting it in a machine shop, there's heat generating that process. The thing catches fire, right? The turpentine residue on it, this thing catches fire. In any case, they're now convinced that they've got a way to cast it in a much larger form. It's not a button anymore. It's now like a Nalgene bottle size thing.
And it's worth noting, we talk about them holding it, cutting it, and it's uranium, and it may sound dangerous, but at this stage, it's actually not dangerous and it's relatively safe.
Yeah, I would say many of the health effects were not super well known at this point. But this was back when science was real and people weren't afraid to get their hands dirty. And but you can actually handle uranium. It only in sort of a room temperature state emits alpha particles, which don't even penetrate the skin. Really, the problem is when you eat it. So you don't want to be ingesting it, which you start cutting things open and it's hot. Now things are going to get volatile. Actually, consuming and ingesting uranium oxide is very bad because it will absorb other sorts of rays and it'll emit electrons and cause other reactions to become possible within your body.
The book talks about over the course of his life, working for years like he did on this stuff, he actually got some uranium in his lungs and it's led to some health complications. But at the time, it was such a paramount thing that they're going for. And what I think is pretty amazing in the story, like, okay, so they've made an ingot. Still, when they now are thinking about how to continue to scale this, they start talking to other people from industry and others. And there's this quote by this person from, I can't remember if it's from Mallinckrodt or whatever, one of these industries. And he goes on to say, like, everyone I am sure felt it to be a futile to look at a couple of college professors for the production of any significant quantity of metal. And yet that's exactly what they did. They realized they just had to scale this thing. So instead of using these little, pipe bombs essentially for the thermal reaction, now they've got these big pit furnaces. And the stories about that are completely wild because they're talking about like, they didn't always work. Sometimes these reactions would get a hot spot and it would not remain enclosed. And you have liquid hot molten metal squirting across the room. In fact, there's actually a fire at one point where there's 3,500 pounds of this uranium in this building and it caught fire. A bunch of it was damaged. And when the firefighters come, they don't have the security clearance to enter, right, to fight it. In any case, they do figure out how to scale it up. And remember, the original price that Compton was willing to pay for pure uranium was $1,000 a pound. At this point, they've already got it down to $1.50 per pound. So orders of magnitude reduction. In fact, in the original Chicago pile experiment, inside that giant pile of uranium was 4,000 pounds of pure uranium that came from Iowa State, which is crazy. I am a professor. Like, I know that we do things, we joke about actually scaling things into the real world, and we make like milligrams or grams at a time. The idea of making 4,000 pounds of anything is so cool. And some of the stuff he did to achieve it was motivated by interesting sources. Like, for example, they have a lot of calcium metal, but you have to chop that calcium metal up, and they didn't have a clever way to do that. And then he has a friend who works for the city of Milwaukee's sewage department, I guess, and they have this giant machine that they call the garbage hog. Think of like a garbage disposal in your sink. And they realize like, well, gosh, we could take that. In fact, there's this quote where it says, he told Spedding, quote, "They're big machines that you throw shoes or anything in it. It just cuts it all up, even like a little tea kettle, anything." And sure enough, they're able to throw the calcium in there and out come a bunch of small pieces, which is helping them scale this even to lower costs. They do eventually move from calcium, by the way, to magnesium. It is technically a better reactant, although it'll be a much more volatile one. That's when they started seeing a lot of the explosions where the reaction would get out of control and it would lead to some of these problems. And that's what eventually led to the big fire, which eventually led to the fast feed operation where they tried to now fireproof the building. Eventually, though, this just doesn't belong at the university. This needs to move out to industries, and so Mallinckrodt and DuPont take it over, but not before Ames had actually made 653 tons of pure uranium by the time they handed it off, which is absolutely incredible. And they'd driven the cost down to just over $1 per pound, which is incredible. So, Andrew, and this to be all great because you've got pure uranium, but the little I know about uranium tells me that there's like enriched uranium, for example, right? There's different isotopes. So which one do we actually need? Which ones were they looking for? How do they go about changing this pure uranium from Wilhelm to what they eventually needed?
Yeah, I didn't see Oppenheimer, but if you recall that the two bombs they made, one of them was what they'll call highly enriched uranium bomb, the other was a plutonium bomb, and there's actually quite a big difference. Plutonium actually doesn't exist naturally; you can't go and mine it, so it has to be created from uranium. And how does that process look? And why would we even want enriched uranium in the first place?
Yeah.
You're talking about the difference between plutonium and uranium. Just one fun little, I hate to do this, Oppenheimer cut-in. When they're adding the marbles, the uranium bowl is a massive fish bowl. The plutonium is a little wine glass.
So do you need less for the same type of bomb? You don't need as much fissile material?
Plutonium is much more efficient from a fission standpoint, and so that's why it's desirable.
I see.
But it's a little more challenging to make. But before we even get to that, let's talk a little bit about enrichment and why that would be necessary. So in its natural abundance, uranium has a couple of isotopes, but the main ones that are of importance and the main ones that are really practically useful are uranium-235 and uranium-238. 238 is what's most abundant. In fact, it's very abundant. 99.3% of the uranium that you find in the Earth is uranium-238. But 238 doesn't fission spontaneously when struck with a neutron. It's the 235, which only makes up about 0.7% of natural uranium. So in order to make the bomb that was made out of uranium, they wanted to get to 90% enrichment. So they needed some way to actually separate the 235 from the 238. Turns out that's about a 1% mass difference, so it's quite challenging. And this is what Oak Ridge was doing. They had this massive facility, spanned about half a mile, 6 stories tall, where they just created a uranium fluoride gas. This is UF6, high vapor pressure, so it can be, with a little bit of heat, turn into a gas pretty easily. It's actually quite nice. It behaves like an ideal gas. And they passed it through like 3,000 different gas diffusion chambers.
No way.
Where they're basically just relying on the differences in weight to slowly separate it out. Now we use centrifugal processes for this, but back then this was deemed the most efficient way.
I've always heard about centrifuges and like the enrichment of uranium. I had no idea what this was actually talking about. That's fascinating.
Yeah, essentially at the time they tried centrifuges, but they couldn't get it to be efficient enough. They just didn't quite figure out exactly how it was going to work. Now they rely on convection to separate the heavy from the light, and the centrifuge also furthers the separation. It's still not that efficient, but it's much more efficient than what was happening at the Oak Ridge K25 facility. Now plutonium, in order to get that, you have to use what's known as a breeder reactor. To actually get to plutonium, you'll actually want to start with uranium-238, which is much easier to do. That's probably what they were using these ingots for. When you bombard that with a neutron, it will become uranium-239, which is unstable. It will beta decay, that is lose an electron, down to neptunium-239, also unstable. That will then beta decay again to plutonium-239. And so what they do is they have reactors with fissile material, that's the uranium-235, enriched, it's some sort of enriched uranium to some extent, and then they have a blanket of uranium-238 around it that is being bombarded with neutrons.
So we've talked about uranium. Now we've talked about enriched uranium, but I guess let's deal with the last state that I know of. What is depleted uranium, Andrew?
Don't they use that in guns?
They do, yeah, I know that. I want to say that the A10's 30-millimeter cannon actually shoots depleted uranium rounds.
Like the rounds themselves?
Yes.
And it's not just because of the density? I know, obviously, higher density, more damage, right?
Yeah, the density is the reason that they use depleted uranium rounds in the A10. Because they're trying to destroy tanks with it, as that is one of its main purposes, having these heavy, dense rounds allows it to penetrate armor and actually stop the tank and neutralize it. But interestingly enough, the United States' tank, the M1 Abrams, uses depleted uranium shells and also has depleted uranium armor. Because obviously, if you're trying to stop this big, heavy, dense projectile, it helps to have armor made of the same material.
Yeah, going back to our armor plating episode, it's a horrible business to get into. It's easier to make denser projectiles, very hard to stop them. So depleted uranium is a byproduct of the enrichment process. As you separate it out, you're actually slowly generating a lot of pure uranium-238, or at least close to pure. So if it naturally occurs with about 0.7% 235, depleted uranium after that processing is about only 0.3% of what remains. So there's not too much fissile material, certainly not enough to be useful. And as you mentioned, it is really dense. Tungsten is a little bit denser, but tungsten's actually very hard to work with. It's very difficult to machine because of it's so hard, and uranium is very castable and shapeable, and so you get that penetration, but it's much easier to work with. And so depleted uranium is used in a lot of armor-piercing applications, not only because of that density and ease of workability. We also have a lot of it because of all the enrichment processing that we've done. But it has other applications too. In a lot of, it's actually used often to shield other radioactive materials because it's so dense. It absorbs radiation quite well.
Yeah, talking actually about tungsten, what's really interesting is when they were developing the A-10, the cannon on it, they knew it had to pierce, at the time, the people they considered their enemies' armor, so that would be China and the Soviet Union. And so they thought tungsten was the go-to, but the problem was that the majority of the tungsten at the time was found in China and the Soviet Union. And so they had to come up with a different kind of material, and so they turned to depleted uranium.
And they were actually using uranium in military applications before the Manhattan Project. They knew of its existence for quite a while. And so during World War I, there was a molybdenum shortage, and they needed that for their tank barrels. And so the U.S. government put a bunch of money into universities to start researching ferro-uranium alloys because of their density. It was a good substitute for molybdenum in these steels.
One of the unintended benefits, too, of using depleted uranium in ammunition is that once it explodes from the main projectile, the fragments will actually catch fire and turn into incendiary rounds, essentially.
Well, think about it. Like when the round hits it, it's going to deform. Little bits of that powder metal is going to come off. And we've just learned that when you get the surface area high, small powders, it's catching fire, right? It oxidizes so rapidly. That's fascinating, though.
Mm-hmm. Now, there are some concerns over depleted uranium. The Gulf War was the first war to actually see those being used in mass. And so there was actually a lot of concern of whether this was causing various diseases among combatants. There's something called Gulf War syndrome, which just refers to some very specific side effects that were witnessed in a lot of the veterans of that conflict. But after quite a number of extensive investigations, it seems that the depleted uranium is not so much the cause, or at least is not the primary cause, and rather other chemicals and pesticides that were being used in the region seem to be more likely the issue.
Oh, fascinating. Okay, this was a fascinating episode. I think there's more to talk about here. I don't think this is the last time we'll be talking about nuclear power, nuclear weapons. But what I think is really cool is that Wilhelm was this underrated character in history, and it's been fascinating to learn about his life. If you get a chance, if you want to read more about it, the book is called Wilhelm's Way. The author is Teresa Wilhelm Waldorf. This is his granddaughter. It is well worth the read. I think it's fantastic. She does a good job of, like I said, capturing the chemistry in a way that is fun and accessible. Like as a scientist, I really enjoyed it. It was fun to see the trial and error and see how he tackled problem after problem into this approach. And what's cool is also learning about what made him the person he was. His backstory is fascinating, and what he did after the Manhattan Project. For example, 1952, the dude invents zircaloy. We've talked about zircaloy on this podcast. Like, very influential person, had a fascinating and meaningful life. So if you want a good book, Wilhelm's Way, we'll put a link to it in the show notes. Today's episode is brought to you by American Elements, the world's manufacturer of advanced materials. American Elements, now invent. The Materialism podcast is also sponsored by Materials Today. Visit materialstoday.com to stay up to date with the latest happenings in material science field and read some of their fantastic articles. We always do. In fact, you can also head over to elsevier.com to find out more about their journals, books, conferences, and programs. We appreciate what they do to make this show possible.
Well, as always, thanks for listening. If you have a moment, please subscribe to us on YouTube. It's at Taylor Sparks. Give likes and comments on wherever you listen to your audio podcast, whether it is Spotify or wherever. Please give us reviews, ratings. It helps get us out to a bunch of new people.
Train that algorithm.
Oh, yes. Finally, you can check us out on Instagram at materialism.podcast.com. We post the artwork. We sometimes post some other cool things on our stories. And also, we are always responsive on there, so you can give us a message and we'll respond back. You can also reach out to us at materialism.podcast@gmail.com. And also, we want to give a big shout out to Alphabot and Kolobyte for making the music. They make a ton of synthwave music. You can check them out on Spotify and YouTube. Have a good one, everyone.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world. and are bound only by their imaginations in manipulating those materials.